So class, we're back. Let's go to the part two of our three-part series of the physiology of vision. So I'll now share again my PowerPoint, okay, for a while. So we are now in um, part two of the physiology of vision. Part two is receptor and neural function of the retina. Okay, we have the layers of the retina composed of from the outer part of the eyeball. This is the eyeball, for example, and this is the outermost part. We have the pigmented layer, outer nuclear layer composed of the rods and cones, outer flexiform layer here, which contains your horizontal cells, the inner nuclear layer with some cells, bipolar, amacrine, and the inner flexiform layer with the um, extensions of your amacrine cells and bipolar cells. And lastly, we have the ganglion cell layer, which will, if you collect the nerve fibers, will produce your optic nerve. Okay, so here it is. This is your retinal layer. The pigment layer is nearest the outer part. Okay, and the ganglion cell nerve fibers will form your optic nerve that goes this way. Okay, your optic nerve. Okay, so if we have the light direction of light, if we have the light rays, or if we are looking at when an object is being um, looked at, or if we're looking at an object, the light rays will go from here to there. So it has to pass through this thickness. Okay, so like this one, thickness from the light rays coming from here, going there, it passes through the several layers of the retina. Okay, but it has a part which we call the macula and fovea or fovea. Macula, the center of it is the fovea, which doesn't have any cellular components. So light directly goes there. So the area where you have the uh, clearest focus, where it is most clear, is in the area of the macula and fovea, which contains only cones, no rods, no ganglion cells, no amacrine cells. So the light directly goes there. So the vision is clearest, most focused here in the macula, specifically the fovea. Okay. The rods and cones are composed of this structure, outer segment, inner segment, and this is the part where you have the outer limiting membrane, and this is the part where it synapses with the other cells. Okay. The rods and cones, this is a rod, this is a cone, and there are several membranes interfolded inside the rods and cones. Okay. Okay, let's go back. So the pigment layer, what's the purpose of the pigment layer? Okay, the pigment layer is actually a darkened area with melanin. So it absorbs light. So if you can liken it to, what is its purpose? You can see this, the defect here is most seen in albinos wherein they don't have pigmentation. Okay, so what happens when the light rays go in, it's scattered, so there is lessened contrast, there is lessened visual acuity. So the albinos usually have visual acuity of only 20 to 100 or 20 to 200. Okay. The pigment layer also contains the vitamin A, where there would later on be an exchange from here to there. Okay. And then the blood supply also comes from this area, the choroid area here. Okay. The blood supply comes from here, choroid area near the sclera, and the central central retinal artery here. Okay, so you have dual supply, the central retinal artery, and the supply coming from the choroid plexus here. So so this layer of the retina, it contains the rods and cones. Okay, and we showed you a while ago how they look like. And this one contains the vitamin A. Okay. Rods and cones, rods and cones. Okay. So whenever light strikes the rods and cones, the light energy makes these chemical changes into this retinal. And then after a while, this is again reformed into your rods, in the chemicals, photochemicals in the rods and cones. So it's the same with cones, rods and cones. This is the chemical reaction that happens inside. The only difference between rods and cones is that in the rods, you have your color pigments instead of rhodopsin. Okay, so for rods, you have the rhodopsin. For cones, you have the color pigments, but it undergoes the same chemical reaction. And vitamin A is needed especially for rod vision, for the vision at night. Okay, so you have what you call a night blindness when you lack vitamin A. Okay, when you have excitation, okay, the excitation of your rods and cones is more of hyperpolarization instead of depolarization. So what happens? So this is the normal state. Okay, negative inside, positive inside. There is entry of sodium and potassium normally, and the moment, okay, in the dark, for example, in the dark, the rods, the moment light strikes the rods, there is exit of sodium out and closure. Okay, so this dark, there is what? Exchange of sodium in and out. But the moment light strikes the rods or the cones, sodium goes out, it locks it out, and there is hyperpolarization. So the reaction in the simulation of the rods and cones is hyperpolarization instead of depolarization, as what happens in other sensory reactions. Okay. Okay. So what happens in the outer segment, the rhodopsin is activated. It activates the G protein transducin. This G protein transducin will now activate the cyclic GMP phosphodiesterase, and this in turn activate the cyclic GMP to form 5' GMP, okay, and it closes it closes the gate which makes sodium enter, and so the rods and cones are hyperpolarized. Okay. For the cones, okay, we have three kinds of cones. one that is in charge of seeing blue, cones that are in charge of green color, and other cones which are in charge of red color. So if you stimulate the blue cone, you only see blue. If you stimulate the green cone, you only see green. And when you stimulate red cones, you see red cones. But if you stimulate at certain wavelengths, then you see either violet, a combination of your blue and green, green, yellow, a combination of your green and red, and orange, okay, and so on. Okay, the rods, the maximum peak of rod stimulation is at 505 wavelength, nanometer wavelength. Okay. So here, what wavelength is stimulated when you see green? 67% of green cones are stimulated. Okay, yellow, 83% green and 83% red. In order to see orange, it is 42% green and 83% red of cones stimulated. Red is 99% red cone stimulation. Okay. Let's now go to your adaptation. Okay. Whenever you enter whenever you come from a very bright, whenever you come from a very bright environment, bright lights, your the rods and retina will be degraded. So if you've been in the bright area for a prolonged time, okay, all the rods and cones will now be degraded into retinals, opsins, and other simpler forms of the biochemical components. Okay, when you go in, so you now become less sensitive to lights after being in the light for a few hours. Okay, now you go in, and then you suddenly go inside a room. Okay, you will note that you are suddenly blinded because from the lighted room into the darkened room, the rods and cones are still not ready to function because they are in their degraded forms. So it takes time. Okay, this is now your dark adaptation. It takes time. It takes time for the cone and rods to go to their non-reduced products to become cones, activated cones and rods again. And so you call this your dark adaptation. Okay, the cones adapt within 10 minutes in the dark area. Okay, while the rods have a longer time to adapt in the dark. Okay, so you can. What does it mean? In the dark, you can see only up to a certain number of colors because of the darkness. But in the white and black, you can see clearly after a few minutes or after 1 hour in the dark. So do you call this your dark adaptation? Okay. You also have a pupillary adaptation to light and dark situations. Um, darkened or lightened room situations. You can see this in like in the like going inside the movie house or coming out of the movie house. Okay, from the movie house, it's very dark. You suddenly go out. You suddenly go out of the movie house, and it's very bright. Okay, um, So the brightness will first initially blind you. It is flashes so much light, it blinds you until the pupils constrict. So that this pupillary constriction is now an adaptation to the sudden exposure to light. Okay, okay, let's come from outside the movie house, go inside the movie house. You initially, from a lightened area like the outside the movie house, it's very bright, and then you suddenly go inside the movie house. It's very, very dark. The pupils will now enlarge so that you can see more light coming into the pupils. There would be more light coming into the pupils, and now there is adaptation in the dark. So you have retinal light and dark adaptation. You also have pupillary light and dark adaptation. Okay, let's now look at color, how we see color. Okay, in order to test if we have color blindness, these two charts, Ishihara charts, are shown to you. So when you look at this, what number do you see? And when you look at this, what number do you see? Okay, write it down now, and then I'll ask you later what numbers you see. But I cannot listen to your answers. Anyway, for this, you're supposed to see, if you have normal vision, you're supposed to see number 74, okay? If you have red and green color blindness, this you will see number 21 here, okay? For this one, you should see, if you have normal vision, number 42. But if you have red blindness, red color blindness, you'll see this as number 2, okay? And if you have green blindness, you can see this as number 4. If you are red-green colorblind, you don't see anything in here. So normally this is 74, normally this is 42. For red-green blind, you see this as 21. For red blind people, this is number 2 only. For green blind people, this is number 4 only. Okay? How did you score here? Normal or colorblind? Okay. Color blindness is recessive X located in the X chromosome. So this is sex-linked. It is carried by the mother because a male child, so this is usually manifested in the male child. And because the male child doesn't have the second X chromosome to counter the X abnormal gene in the X chromosome, then the male child will be colorblind while the mother is the carrier. Okay. So this is the neural organization of the retina. In this area, you have how many layers? The cells of rods and cones, horizontal cells, bipolar cells, amacrine, and the ganglion cells. While here, this actually represents the fovea or the macula, specifically the fovea, wherein you only have cones, no rods, and they are directly connected to the bipolar cells and then to the ganglion cells there. Okay, so you have the best visual acuity in this area in the fovea because there are no other cells than cones, bipolar, and directly to the ganglion cells. So here you have 4 layers, 1, 2, 3, 4. Before going to ganglion, here you only have 3, 1, 2, 3, or 2 layers actually, 2, 3, before going to the ganglion, 3 layers, okay? what is the neurotransmitter here? Okay. The neurotransmitter um, in the neurotransmitter is actually glutamate. Okay. The others is electrotonic conduction. It's done through electrotonic conduction. So from here, you have you have an action potential in the ganglion cell. Transmission is through electrotonic transmission from the rods and cones, electrical conduction. There's hyperpolarization, and there is electrical conduction to the horizontal bipolar amacrine. And by the time it reaches the ganglion cells, you have the action potential, okay, which is like the other sensory cells. So if you have a graded direct flow of electricity, it allows graded conduction. Okay, so the amount of conduction that is transmitted depends on the amount of or intensity of light that reaches this. So it is not like the all or none reaction, but graded. So it can be lighter, darker, brighter, more contrasted, gray, more red, more green. So there's a graded conduction. Okay. You will also note, okay, that you have horizontal cells here, which are usually inhibitory. So if this is, so it transmit inhibitory stimulation. What do we mean by this? Okay, so if this, for example, this one is the red cone, it stimulates the ganglion cell for you to see a red color. Okay, it inhibits the green cone and the blue cone, so you see a very sharp red color. But if there is no inhibition in the red and the blue, in the green and blue, okay, so for example, blue, red, green are all stimulated, and they all stimulate ganglion cell. What do we see? White light. The ganglion cell will now interpret this as white light, because white is actually the color that you see when all red, blue, green colors are stimulated. Okay. If you stimulate only red and green, what do you see? You stimulate red and green, you actually see yellow there, or orange, depending on how much green is stimulated. So that's what happens when you when the cones are stimulated. There is a stimulation and there is inhibition, excitation. So while red color is getting excited or stimulated, there's lateral inhibition to the green color or blue color. So there is sharpening and contrast of seeing a red color. So this is red. This is an example here. Okay, light being on the red cone inhibits, and then there's inhibition of the green cone and the blue cone. So you have a very sharp red color, looking at this very sharp red color. It is said that amacrine, okay, so this one, lateral horizontal cells with its lateral nerve fibers, okay, and horizontal and bipolar cells with its horizontal fibers cause inhibition to the lateral or to the other cells, while the amacrine cells is the one that sometimes analyzes visual signals, and this is inputted into your ganglion cells. Okay. In this area, you usually have 60 rods to 2 cones. Okay, so there are 60 rods to 2 cones, and they go to your ganglion cell. Okay, but in the fovea, you have only cones there, and they no rods at all, and they go directly to the ganglion cell, and so there is visual acuity in the fovea. Okay, so I think that's it for the part 2 of our lecture, which is receptor and neural function of the retina. Okay, we'll cut it again at this point, and let's come back for the third part, the central neurophysiology of vision, in a while. Okay, see you in a while. Go out, walk, exercise, eat, whatever, and then come back here. Okay?